Christopher Cashen, who is going to speak about the topology of the contracting boundary of groups.
Okay, so thank you everybody who made it to talk number 29 of this workshop. Well done. So before I begin, let's thank the program organizers, Gulnara, Cornelia, Alessandra, and Nicola, and the workshop organizers, Mark, Gulnara, Cornelia, Eric, and Danny. Okay, so I'm going to talk about contracting boundaries, and this is joint work with John Mackay, and it builds on work with Argenteva, Gruber, and Hume that you've heard about from Dominic and David already in the last 2 days. So the goal, the very broad and vague goal, is to do boundaries of hyperbolic groups. For non-hyperbolic groups. And so that's vague. What exactly do we want to do? Well, the problem is that you have to be a little bit vague because there's so much that you can do, right? The hyperbolic groups and their boundaries have so much structure that if you're going to try to do something useful for non-hyperbolic groups, there's probably going to be some kind of trade-off involved. So if you want to get certain properties that you would have for hyperbolic groups, you probably have to give something up. And so, for example, of course, there have been lots of attempts to do useful things, and they've had certain amounts of success. Like in cat zero spaces, you have a nice visual boundary. But there are these examples of Croak and Kleiner of a group, just a single group, where it acts geometrically on two different cat zero spaces that have non-homeomorphic boundaries. So there's no way to assign the visual boundary of a cat zero space to a particular group. It doesn't have, so groups don't have cat zero boundaries, even if they admit nice actions on cat zero spaces. The boundary is not a property of the group, it's a property of the space on which it's acting. So that's one thing that we'd like to get out of this. We'd like to get, in what I'm going to talk about today, we're going to get a boundary that belongs to the group. So it's going to be quasi-isometry invariant. And the idea is Studa, Charney, and Sultan. And so this is the contracting boundary. So they were looking at cat zero groups, and in particular right-angled Coxeter groups. And they said, okay, well, there's no well-defined visual boundary of this cat zero space, but maybe the problem is with the flats. Maybe the problem is with the non-positive curvature. And there's a well-established idea in cat zero spaces that you have some geodesics that behave very much like hyperbolic geodesics, but you also have flats. And so their idea was, let's only look at the hyperbolic things. So X was, for them, X is cat zero space, and they define a contracting boundary. And they did it the way that you would try to do the visual boundary is they picked a base point, but then they said, let's look at contracting geodesic arrays. And mod out by bounded Hausdorff distance. So you have some subset of geodesic rays, so you think of these as sort of the hyperbolic directions. You have some base point, and these are the hyperbolic ways of going to infinity. And so that's a set. That's what this boundary is going to be as a set. And then you have to come up with a topology for it. And so they succeeded in finding a topology on this that's quasi-isometry invariant. But, like I said, there are going to be some trade-offs. So their trade-offs, so pro, this boundary is QI invariant. Con, well, it's not compact anymore. You haven't looked in every direction, right? You've purposely ignored directions that are going out into flats. So you shouldn't expect the boundary to be compact, and typically it won't be if the space wasn't hyperbolic to begin with. So I'll be vague, and then later in the talk I'll give a specific example of what I mean, but in this boundary you lose some of the geometric intuition. And a closely related problem is that, in fact, their boundaries are not first countable. And so that's very different than the boundary of a hyperbolic group. Nevertheless, some useful things have been done. So Charney and Sultan paper. So this is all very recent work. So their paper, like I said, they were interested in right-angled Coxeter groups, and they produced this quasi-isometry invariant boundary, and they had some examples where they could compute not exactly what the boundary was, but enough about its topological properties to actually distinguish between some quasi-isometry classes of right-angled Coxeter groups. So Matt Cordes generalized their construction and got rid of the cat zero condition. So he defined this boundary on arbitrary geodesic metric spaces. And Devin Murray, again, was looking at cat zero spaces, and he proved some more detailed theorems about what the topology of the space is like and what the group dynamics are acting on, a group acting on its cat zero contracting boundary. And then Cordes and Hume, they use this kind of boundary of Cordes in the general case to define quasi-isometry invariant notion of dimension related to the boundary, and they use this as a quasi-isometry invariant for some classes of groups. So some useful things have been done with this boundary, but the idea of the talk today is maybe the trade-off that we made here wasn't the best possible deal that we could have gotten. So the theorem is if you have a finitely generated group, there is a different topology that seems better. So I'll follow Damien's advice, and we have a simple idea of how to define a new topology, and we're going to give it a fancy name. So we're going to define something called the topology of fellow traveling quasi-geodesics on the contracting boundary of a finitely generated group. And the conclusion is going to be that it's still quasi-isometry invariant, but it's also metrizable. So I'm not going to claim that this is the right topology for this object. It seems pretty good. When you see the definition, it feels geometrically fairly natural, a natural thing to try. I'll ask a question at the end about what some other options might be. But at the very least, this should be like the beginning of the story. You shouldn't think that this is settled, that the topology that Charney and Sultan used is really the one that you ought to be looking at. So there are, it seems, better alternatives. And hopefully we can find some more useful things to do with these boundaries. So David introduced contraction. So I'm supposed to be topologizing instead of contracting geodesic rays. So let me remind you what contraction is. So X is a proper geodesic metric space. Z is going to be a subset in X. And we have a closest point projection map from X into subsets of Z that just send X into the set of closest points. So about this map, so I want to require that no point has empty image. In practice, the things that we want to project to are all going to be closed and the space is proper, so we don't have to worry about this. In more general settings, you can say make it the almost closest points and just add a constant here, but that won't be important today. But also notice, as David said, we don't bound a priori, we don't bound the diameter of a projection. So as the point x that we're trying to project down to z gets farther and farther away, the diameter of this projection might be growing linearly even. So another terminology, so function rho so if I talk about a sublinear function, I mean that it's non-decreasing, non-negative, and that the limit of the function to r goes to 0 as r goes to infinity. So now the definition is a function, if I give you a sublinear function rho, then I say z is rho contracting if for every pair of points that are, so yeah, the picture again is x is going to be the center of the ball and I want y to be a point in the ball where the radius is the, so here's z, here's x, here's a ball around x that's tangent to z, I mean, so the radius is exactly the distance, and y is just some other point in this ball. And the conclusion is going to be a bound on the diameter. In terms of the distance to the, so x, you project x down to z, closest point projection, and you get some subset of z. And y, you project down, and you get some subset, again, of z. And then this diameter is what's bounded. So this is less than or equal to the radius of the ball. So as the balls get big, since the function rho is sublinear, the projections get smaller and smaller relative to the radius of the ball. And so this comment that the diameters of projections of single points aren't bounded in general, it could be that when you project this ball and see the diameter of the projection, it could be just the center of the ball is realizing the entire diameter of the projection. It can be just that the projection of a single point is sort of the worst thing that's going on. So examples. So conveniently, David talked a lot about many different examples. So there are lots of natural examples. The most familiar one is if x is hyperbolic, then some subset z is contracting, meaning there exists some sublinear function rho so that it's rho contracting, if and only if it's quasi-convex. And I mentioned in cat 0, so this idea was already around in cat 0 spaces, that geodesics should be either sort of living in a flat or hyperbolic looking. So in fact, in cat 0 spaces, you're either contracting or you, well, spend a lot of time in flats and so are very far from contracting. So here's another definition that David gave, strong contraction. So we'll say a set is strongly contracting if it's contracting and the contraction function is a bounded function. So hyperbolic groups, when you have a hyperbolic space and you project to a quasi-convex subset, this is going to be strongly contracting, and the contraction function is going to be bounded just in terms of the hyperbolicity constant and the quasi-convexity constant. Similarly, in a cat zero space, so in hyperbolic spaces, geodesics are uniformly contracting. In cat zero spaces, they're always strongly contracting, but not in a uniform way. So it depends on how long you spend traveling through flats. That's going to tell you how contracting you are in a cat zero space. So other examples, Minsky showed that the axis of a pseudo-Nossoff mapping class in Teichmuller space is strongly contracting. Algom-Kafur proved the same thing for axes of fully irreducible outer automorphisms with free groups in the outer space. The fact about cat zero spaces, I should say, so this goes back to work of Ballman on the rank rigidity conjecture, and then Besvina Fujiwara introduced this contracting terminology in the cat zero case, and then Sultan proved in full generality that Morse is equivalent to strong contraction in cat zero spaces. So Morse. So Morse, the way I'm using Morse is like quasi-convexity for quasi-geodesics. If you have a quasi-geodesic with parameters L and A, then there's some function mu that tells you how far that quasi-geodesic is allowed to stray away from Z. And so theorem. So I said Sultan proved in the full generality that Morse is equivalent to contracting in cat zero spaces. In fact, this is true always in geodesic spaces. So this contracting function really is a reformulated version of the Morse property. So let me draw an example of contraction that's not strong contraction. So here's a base point. And here's a geodesic ray Z. And then the space X is going to be, I'm just going to add some detours coming off this ray. And when I add them, what I'm going to do is the part where they overlap the ray, make that length I for I growing, and then make the length of the whole thing be 4 times 2 to the I. And now the idea is where does projection go wrong? Well, there's a point on each of those detours that's farthest away. And actually, you catch that point in your ball when you're a quarter of the way around. So the distance from X to the axis Z here is 2 to the I, and then the distance from X to Y is also 2 to the I, right? So the diameter of the projection of X and the projection of Y, well, Y projects down on both sides. So the diameter is this entire length I. And I is log 2 of the distance from X to Z. And so, in fact, this Z is log 2 contracting. Okay, and so David and Dominic were talking about infinitely presented small cancellation groups. So this, when we introduced this definition, more general definition of contraction, this is the kind of picture we had in mind, because in these infinitely presented small cancellation groups, you have these arbitrarily large embedded geodesic loops. And the picture then you should think of is like this. So in all of these other cases of strong contraction, the philosophy was the space is more or less hyperbolic, except you know there are certain regions where it's not, right? In cat zero spaces, there's the flats. In mapping class groups, in Teigmuller space, you have these product regions. And so you know if your geodesic is supposed to be hyperbolic, it should avoid these non-hyperbolic regions. And that's the same thing that's going on here. I have these big embedded loops. I know hyperbolic spaces don't have big geodesic loops in them, so I ought to avoid them if I hope to be geodesic, if I hope to be contracting. Now, it's not quite as bad as the other cases, right? I don't have to avoid them in a bounded way. I can make my intersections grow larger and larger as long as I'm seeing a relatively small part of the loop, because I don't get the bad projection until I get all the way to the end of the loop, basically. So let me also not leave you with the impression that the difference between strong contraction and this other sublinear contraction is just about non-finitely presentable groups. So this shows up naturally in a lot of examples. For instance, Daniel Woodhouse told us about tubular groups, and he mentioned these examples of Brady and Brightson, so snowflake groups that realize a dense spectrum of Dane functions. And so in such groups, you have big loops, bigger and bigger loops, and the Dane function is some high degree polynomial, so these loops are hard to fill. And so if you want to fill such a loop, you have to attach sort of a big disk with a lot of area on it. And so these big loops, these larger and larger loops that are showing up, play a similar role to this. So you can show in these snowflake groups, which are finitely presented, nice tubular groups, that there are geodesics that are contracting but not strongly contracting. So this notion, this more general notion of contraction, shows up in lots of places. So another thing to mention is we also showed in the same work with Gulnara and Dominic and David, so the idea of strong contraction is not preserved by quasi-isometries. So if you're thinking that all the familiar examples have strong contraction, we ought to do that. You can't hope to succeed defining a contracting boundary in general with strong contraction, because you won't even preserve the boundary as a set, let alone topologically. So you really need this weaker version of contraction, and it is quasi-isometry invariant because it's equivalent to the Morse property, which is quasi-isometry invariant. So here's the sort of key technical lemma that's going to make most of the arguments in the paper work. So suppose that Z is a row contracting set. All right, so before I do that, I should say, given rho sublinear L greater than or equal to 1, A greater than or equal to 0, there exists a kappa depending on these, and also a kappa prime, so that if Z is rho contracting and gamma is a continuous LA quasi-geodesic ray based on Z, then there are two possibilities. Either gamma is trapped by Z or it escapes. So if it's trapped, what this means is the subset of Z that comes within distance kappa of gamma is unbounded. And in this case, then actually gamma is trapped inside the kappa prime neighborhood of Z. And the other option is that gamma escapes. Okay, and so that's the opposite. So there is some last time. There's a bound on how long it stays kappa close to Z. Let's make Z be, all right, so this is nicer to say if Z is a geodesic now. So if Z is a geodesic, then there's a last point So not only is there a last point, but then we want to also say that gamma escapes quickly. Escapes quickly means the following. So here's gamma, quasi-geodesic. Here's some point where I don't know what gamma looks like yet. And here's gamma far away after it's escaped. And suppose I tell you there's some point here, x and z, and some distance here, j, greater than kappa. Then there's an explicit bound on where the escape point was. So this distance is less than or equal to 4/3 j plus some constant depending on rho and L and A. So what that means is that what gamma has to do is something like this, where this distance is kappa. It can't do this. Okay, so, and this is good, right? This picture looks hyperbolic. I have this quasi-geodesic, and it's closely tracking z until at some point it gets far enough away, and then once it gets far enough away, it goes away almost as fast as it can possibly go. So let's take a guess at a topology now. So here's a topology that's not going to quite work. It's the usual topology that you would try to put on the boundary of a hyperbolic group. So as a set, we're just going to have the set of contracting geodesic rays at some base point, modulo Hausdorff equivalence. And now the topology is going to be, let's define eta is, so I'll be a little bit vague here because this isn't the topology that I really want. So I'll say eta is close to zeta if geodesics in eta and zeta closely fellow travel for a long time. Right, so here's your base point, here's points zeta and eta out on the boundary, and I pick right, those are equivalence classes of geodesic rays, so I pick representatives, and they're close in the topology on the boundary if the rays sort of stay close together for a long time before they finally diverge. Now, why is that quasi-isometry invariant for hyperbolic spaces? Well, suppose you have a quasi-isometry from the left side to some other space on the right side. You had these two geodesic rays. You push them forward to quasi-geodesic rays. And not only quasi-geodesic rays, but uniformly quasi-geodesic, because the quasi-isometry constants are just whatever came from the map. And you had, pick, say, 2 points here where whatever this closeness threshold that I didn't tell you, these are the points where you exceed that closeness threshold. Okay, so push those forward. They might get stretched out by the quasi-isometry, but you know how much they're getting stretched out because it's just the quasi-isometry constants. Now, these are quasi-geodesics. Let's straighten them out to get geodesics. You can straighten them without moving them very far because the space is hyperbolic and you knew what the quasi-geodesic constants were. So these 2 points that you were watching, they didn't move very far. And so you know how far apart these points can be now. And then the last thing that you want to do is say, well, because I know this space is hyperbolic, I know if these points aren't very far apart, right? Here they were very close. They moved, they stretched out some in my maps, but not too much, to a controlled amount. And because it's hyperbolic, I'll use the hyperbolic condition to say, actually, these 2 rays still fellow travel for an amount of time that I control because I know these points are pretty close together. So the picture cannot be, it cannot be something weird like this, right? That's not how it would work in the hyperbolic space. So if you draw a geodesic triangle from the base point and these 3 points, it has to be thin. So they really have to fellow travel for an amount of time you can control. And that's what you need to prove quasi-isometry invariance of this topology on the boundary. So what's going to happen for the contracting boundary? You still can start out with geodesic rays. You still push them forward and get quasi-geodesic rays where you can control the constants. It's true that the images will still be contracting, and so you can still straighten them to get geodesics. And if you haven't moved things very far yet, then you want to apply this property like I did at the end to say, as long as I knew those points weren't very far apart, I can control how long they're fellow traveling for. So this key lemma will take care of the last step. So the problem with this approach is the part about straightening. In the hyperbolic case, I knew the quasi-geodesic constants and I knew a fixed hyperbolicity constant. So all of the rays are uniformly contracting, which means I only have to straighten a uniform amount. Because I'm trying to define here close to zeta. I don't want to involve eta in this computation. And that's a problem in the contracting world because when you try to tighten these things, tightening the image of zeta is going to be fine because you know that contraction constant, but you can't tighten eta the way that you want to without using the contraction function for eta. And this is not just a glitch in the proof. This is really a problem. So here's the example. So consider the Euclidean plane minus the ball of radius 1 about the origin, and then take the universal cover. So your space, right, you've punched out a ball, and then you take the universal cover, so you have this like spiral, infinite spiral staircase that's infinite, but it's infinite going out, but it's missing this open ball in the middle, which means you have a boundary curve here, which is a bi-infinite geodesic, and it's strongly contracting. The rest of the space is flat, so this is the only place where you find the contraction in this picture so far. To see that it's strongly contracting, imagine a ball that's disjoint or tangent to this, right? It lives in a half plane. And so when you project, you're going to see at most a semicircle in the image of your projection. So this boundary curve is strongly contracting. The space is cat 0. Okay, and now pick a base point and just pick a radial geodesic. And then I'm just going to start gluing things on. So I'm just making a space here. So at the integer distances along this line, I'm just going to tack on a geodesic ray like coming out of the board on this particular sheet. So now what's my contracting boundary with the topology that I described up here, well, these rays that I've added are all strongly contracting. Right? The contraction constants get worse and worse because the geodesic from the base point lives in a flat plane for a longer and longer amount of time. But once it reaches the point where I tack down this ray and leaves the board, there's nothing projecting to it anymore. Right? So the diameters are all going to be bounded by just however the length of time that it spent in that plane before it started coming out of the board. And there's no, these points fellow travel, but if you look at the endpoints of this geodesic here, these are going to be isolated points in the contracting boundary if we topologize it like this, because there's just none of these contracting rays that I've showed you have geodesics that are fellow traveling those ones. Okay, so now what's the problem with quasi-isometry? Well, we have this pathological quasi-isometry of the plane, which we can apply in this picture, which is the logarithmic spiral. So if you do a logarithmic spiral, this radial geodesic that you had before now spirals out around and around. And it's a quasi-geodesic, and you know exactly what the quasi-geodesic constants are because they just came from the quasi-geodesic constants of the logarithmic spiral map. And these rays that you tacked on, now just let them come along for the ride. And now the point is, this should go this way. Now, say take a point that's far out along this and look at its geodesic. From the base point, the geodesic to get out there, now if it's wrapped far around, it's in the wrong sheet of this spiral. And so the fastest way to get out there is to run along the interior spiral until you're in the right sheet. And then once you're in the right sheet, you go straight to that point. And so the point is you are fellow traveling the core curve, the boundary curve now. You have to fellow travel the boundary curve until you get to the correct sheet. So as you go out along this geodesic spiral, when you want to travel out one of the purple rays, you have to fellow travel that central geodesic for longer and longer times. So this sequence of contracting points, the endpoints of these rays up here, we sent it by a quasi-isometry to something that was converging when it wasn't converging before. And the inverse quasi-isometry will do the opposite. It'll take a convergent sequence and it will make it not converge anymore. So this topology, even on cat zero spaces, will not be quasi-isometry invariant. So you have to change something. So, well, what did Charney and Sultan do? So what they noticed, I mean, in a picture like this, the problem is coming from the fact that the sequence, the bad sequence that you're looking at, is getting less and less contracting. It spent more and more time living in the flat, so the contraction got weaker and weaker. It was tending towards sort of non-contracting things. And that's why you lost control of how closely the quasi-geodesic has to track the geodesic. So what Charney and Sultan said is, let's not allow that. They said just control the contraction constants. And so what they did is they said, let's only look at the part of the boundary that consists of row contracting rays. That you can topologize with this topology that I've now erased. So let's call that topology FG for fellow traveling geodesics. Okay? If you fix the contraction constants, if you bound them, then you have all the good control that you want from hyperbolic spaces. So this subset you can topologize, and then they're going to define the contracting boundary to be the direct limit of these subspaces. Okay, so these subspaces, they form a directed system under inclusion as you let the contraction function grow larger and larger. The direct limit as a set is the contracting boundary that you want. And then the topology that they say is, let's take the direct limit topology. So you take the finest topology that makes all these inclusion maps be continuous. And then the theorem is that this topology is QI invariant. For exactly the reason that I was trying to explain with the hyperbolic groups. You fix the part of the proof that went wrong, and everything else works, and you're happy. More or less. I mean, you have to deal with this strange topology, but this is the heart of it. They fixed this problem that we ran into. So that's the good news. Here's the bad news. So here's an example. Take an HNN extension, just over z squared, trivial HNN extension, meaning you have the commuting generators from the z squared and then a stable letter, which doesn't relate to them at all. Okay? So a picture of this, you have these planes, right? And then you have this other generator C coming off, and then you get to another copy of the AB plane, and so on. And so out at infinity, you have this, the limit of the C's. So at this point, C infinity, and this geodesic from 1 to C infinity, it's zero contracting. So it's strongly contracting, bounded by, with the functions bounded by 0. It doesn't spend any time in these flats at all. It passes right through them, so it's a nice contracting ray. Now consider similar rays where you travel along this C direction for a while, but eventually you take a short walk through one of the flats. But then you return to just traveling along C. So this point is like, say, CA, C infinity. And this point is C squared A, C infinity. Okay, these are also contracting rays. They're one contracting because I spent distance 1 living in one of the flats, and my rest of the time I spent in the hyperbolic directions. And you're following the original ray for longer and longer time before you branch out and go away. So you have nice fellow traveling geodesics. Your things are all uniformly contracting, and this sequence converges the way that you want it to. But the problem is now I want to change the sequence. But I'm going to change it sort of far from where the action ought to be. So consider now the geodesic. It looks like this. I do C for a while. This I should be power. So I do C's for a while, so I'm still hyperbolic, and then I take my short walk through A, and then I return to doing C's, and I do it for as long as you like. And then I decide to take a longer walk through one of the flats. And then I return to being C for as long as you like. This ray is only I contracting, because I spent time I in one of the flats. And the problem with this topology that they put as a direct limit is when you see contracting constants getting worse and worse, you never converge to anything. And so even though it looks like what I did is I took a convergent sequence and I altered it sort of very far out into the tails, this sequence will not converge anywhere now. So this sequence doesn't converge. Okay, so this bothers me. So I didn't like this feature of this topology. But even more than that, so this is the sort of bad behavior that Murray used to show, in fact, that the topology is not first countable. You have too many diagonal sequences that are failing to converge. So this is what I meant at the beginning, where sort of their topology was not so good for your geometric intuition. Geometrically, I want this sequence to converge to C infinity, and it doesn't. Okay, so I'm going to define the new topology now. So before I talked about topology of fellow traveling geodesics, and now this is topology of fellow traveling quasi-geodesics. So there's some choices involved that aren't going to matter in the end, but let me say them. So again, my set, it's convenient now to say, let's take it to be the set of quasi-geodesic rays. This doesn't change anything. This space is proper, so every contracting quasi-geodesic ray is bounded distance from a geodesic ray. So every class here does contain a geodesic. So I haven't actually changed the set at all. Now, for every zeta contracting point, I'm going to fix a geodesic ray. Fact. Yeah.
Sorry, I just missed something. So what's that? Why are quasi-geodesics opposed to geodesics?
Y is because they're contracting. Contracting. Yeah. Yeah, so the contraction function tells you they're quasi-convex. So I'm going to fix a geodesic in each equivalence class just for reference. And then fact, there's a uniform contraction. So for all zeta, there's a sublinear.
This is fixed contracting constants or arbitrary contracting constants?
Arbitrary.
Okay, so you don't have, so they're not uniformly close then, right?
They're not uniformly close, right? Yes.
Sorry, since we're interrupting you.
Sure.
And what about the constants of the quasi and the quasi-geodesic?
It doesn't matter. Okay, so the fact is, once you know that there's one contracting geodesic, then you can say that any other geodesic in the same equivalence class is bounded Hausdorff distance from that one. And then you can say contraction is preserved by finite Hausdorff distance. And not only that, by a controlled amount, so you can compute exactly how contracting the new thing is. So to each point of the contracting boundary, you can assign a contracting function such that every geodesic in that equivalence class is contracting with that contraction function. Okay, so let's fix that and assume this geodesic then is contracting with function rho of zeta. All right, so now I'm going to try to define a neighborhood in what's going to be a topology. And in fact, it turns out that it is a neighborhood in what turns out to be a topology. Okay, so for every zeta in the contracting boundary, and for every r greater than or equal to 1, define the set U of zeta of r to be the other points theta in contraction boundaries such that for all all right, so this is going to be complicated, and then I'll explain it once I'm done writing. So there is the full definition. Let me say it in words now. What are the points eta in U of zeta of R? Well, they're the points so that all of the reasonable quasi-geodesics in eta can't escape from alpha of zeta until after distance r. Where reasonable means continuous and their constants are less than or equal to r. Now, all right, so and then the topology is going to be sort of declare these to be the neighborhood. So a set is open if for every point there exists a set like this containing. So that for every, let's just write it, U is open if for every zeta in U there exists an R, so that this neighborhood U zeta R is contained in U. Now there are things to check, but in fact this does define a topology. And these sets U zeta R that I defined are in fact neighborhoods in this topology, not necessarily open neighborhoods, but neighborhoods. Now there were a lot of choices, so let me say something about the choices. The base point doesn't matter, as you can guess. This choice doesn't matter. These choices don't matter, so if you want to replace them by some functions f and f prime of r, that's fine as long as these functions are increasing and unbounded. Continuous doesn't matter because there's a standard trick about if you have a geodesic that's not continuous, you just pick the integer points and you connect them by geodesics and you didn't change the quasi-geodesic by very much. So you add some amount of error, but it's not very much. And this doesn't matter except that if you made changes, for instance, here, then you added some additive error, you have to include that error here. You can make this as large as you like. The only point is this kappa is the kappa that was coming from the key lemma that's telling you escape when points escape. So you have to choose this to be big enough that zeta belongs to this set. And that's why it's the kappa from the key lemma. So once this is at least this kappa from the key lemma, then what you get is that zeta is contained in this set for all r. So when eta is close to zeta, what that means is all the quasi-geodesics in eta, sort of you can't tell whether they're going to zeta or to eta until you pass distance r, and then they're allowed to diverge after that. And why I claim this is sort of geometrically natural, it's what you would have wanted to do for hyperbolic things, except instead of geodesics, you did quasi-geodesics. And if you're interested in quasi-isometries, you ought to be talking about the quasi-geodesics anyway, right? It was just convenient that in hyperbolic spaces, all the quasi-geodesics were close to geodesics. So you got away with only using geodesics. You probably should have been using quasi-geodesics all along. So theorem 1. So when X is a proper geodesic space, this topology FQ, fellow traveling quasi-geodesics, is a topology on the contracting boundary. For every zeta in the contracting boundary, this set is a neighborhood basis. In particular, this topology is first countable. It's quasi-isometry invariant. Right, again, the problem in the proof before was that quasi-geodesics were escaping too far from the geodesics, and this topology just requires the quasi-geodesics to stay close. It's not too hard to see that the topology is Hausdorff. It's a little more work to see that it's regular. So I promised you a metrizable boundary for groups. This was the properties for spaces. So since the topology is quasi-isometry invariant, it makes sense to define it for groups now. Just define it to be the boundary of any one of the Cayley graphs, and it won't make a difference. Theorem 2. When G is a finitely generated group. So there are 3 possibilities. We don't need the topology here. One possibility, it could just be empty. Of course, if your space doesn't have hyperbolic directions, you're not getting anything out of this construction. So there might not be any boundary at all. It could be that there are exactly 2 directions, contracting directions, and in this case, your group is virtually cyclic. And the third possibility is that the boundary is infinite and the action is minimal for this topology. And minimal means every orbit is dense. And so with a little work from every orbit being dense, what you get is that this topology is second countable when it's a group. So this, you say it's and now the Urysohn metrization theorem tells you if you have a regular Hausdorff second countable space, then it's metrizable. So this topology agrees with some metric topology. We don't know what the metric is explicitly at this point, so this is the next big thing that we'd like to understand is how do you describe a metric on this boundary naturally in terms of the geometry of the group. All right, so let me say in the last minute, I guess theorem 3, just a sort of preliminary result on dynamics, since David was telling us about ping pong and that sort of thing. So there's some version of weak north-south dynamics that can probably be improved. So the preliminary theorem 3 is that contracting elements act with weak north-south dynamics. So contracting element means I have an infinite order element that's quasi-geodesic, and that quasi-geodesic is a contracting quasi-geodesic. And so the statement is, if G is such an element, then for all open sets U containing G infinity and compact K not containing G negative infinity, there exists an N so that you can push K into U. Now, the space is not compact, so you can't put in closed set for compact set, and we know, in fact, that you cannot play ping pong on these boundaries. So there are groups that contain Morse elements, but don't contain free groups. So there's no possibility that in full generality you can play ping pong. So another question would be, can you sort of metrically play ping pong? So Panos told us this morning about a theorem, the Papasoglou and Swenson pi convergence theorem. It tells you sort of what it tells you is that you like to replace K by the set of things that are far enough away metrically from G to the negative infinity. So can you play ping pong once you know that your points are far enough away from the repelling fixed point? So that would be an interesting question to take up here if we get a good handle on what the metric is on this boundary. Okay, so I'll stop here.
Questions?
Yeah, so except for Z, when can you compute this?
It behaves very nicely for free products of groups.
Okay, but are there any like, right? I mean, can you distinguish any Reddy Loring groups with it, for instance, or?
The groups that Ruth and Harold distinguished are distinguished by this topology as well.
Can you say anything about the group if the boundary is infinite? For example, it has exponential growth. Can you get any result about the group?
I'd like to. We don't know yet. Yeah, but this is a good question. I guess I didn't say, I should have said this. So this topology is strictly coarser than Charney and Sultan's topology. So the identity map on the contracting boundary, that's the same underlying set, and the identity map is a continuous map. And when the space is hyperbolic, these all collapse just to the Gromov boundary. Yep.
If you've got a strongly contracting element acting, can you promote the weak north-south dynamics to actual north-south dynamics?
I'm not sure. I mean, of course, these questions are dangerous, right? Because you don't know.
And you already know they're kind of generator free.
Yeah, true. You already know
So
they're
it's not really it's just a test case to see.
Yeah.
Any other questions? Thanks, speaker again.